everyone, this video is an introduction to section 15.1 on double integrals over rectangles and focuses on approximating volumes using a double Riemann sum. Let's start with a review of the definite integral in the single variable setting. Suppose we want to find the area under the curve of y equals f of x for x between a and b. We start by dividing the interval a to b into n subintervals of equal width, delta x, given by b minus a over n. Notice this divides the area we're trying to find into n strips, s1 through sn. We want to turn each of these strips into a rectangle because we know how to find the area of a rectangle. To do so, we choose a sample point x sub I star in each subinterval and allow f of x sub I star to give us the height of the ith rectangle. We note then that the area of each rectangle is found by computing the height of that rectangle f of x sub I star times the width of that rectangle delta x. And if we add the area of each one of these rectangles, that gives us an approximation to the area we're looking for, the area under the curve. And this type of sum, remember, we refer to as a Riemann sum. As n gets larger, this approximation of the area gets better. And so, we take the limit of these sums as n approaches infinity to obtain the definite integral of f from a to b. So we say that the limit of this sum gives us the actual area, that it's no longer an approximation of the area under the curve, but that it actually equals the area under the curve. But because this notation is rather cumbersome, we have a limit, a sum, a subscript I, a star, and a delta. That's a lot of notation for us to carry around. We change the notation. We replace the limit of the sum with our integral sign from a to b. Notice that this integral sign looks like the letter S because it is representing a sum. We then drop the subscript I and the star and have simply f of x, and we replace our Greek letter delta with the English letter d. Now, in a similar manner, we consider a function f of two variables defined on the closed rectangle R, consisting of values of x between a and b and values of y between c and d. And we'll first suppose that we're dealing with the function f of xy, which is greater than or equal to 0. Recall that the graph of f is a surface with equation z equals f of xy. And we let S be the solid that lies above the rectangle R and under the graph of F. Our goal is to find the volume of this solid S. And just as in the single variable setting, our first step is to chop things up. So we first divide the rectangle R into sub-rectangles. We accomplish this by dividing the interval from a to b into m subintervals of equal width delta x, computed as b minus a divided by m, and dividing the interval from c to d into n subintervals of equal width delta y, found as d minus c divided by n. By drawing lines parallel to the coordinate axis through the endpoints of these subintervals, as in the figure, we form these subrectangles R sub ij, and each one of these subrectangles has the same area delta A, found as delta x times delta y. If we choose a sample point, x sub ij star, y sub ij star, in each one of our smaller rectangles, r sub ij, then we can approximate the part of the solid that lies above that rectangle by a thin rectangular box or column with base rij and height given by f evaluated at the sample point, as we see in the figure. The volume of this box is the height of the box times the area of that base rectangle. Now, the height of our box is our function evaluated at the sample point. And the area of the base of this box is that delta A. If we follow this procedure for all the rectangles and add the volumes of the corresponding boxes, we get an approximation to the total volume of S. What we formed now is a double Riemann sum. So we've taken the volume of each individual box as the height of the box times the area of the base, and then added the volumes of each one of these individual boxes, and this gives us an approximation of that volume of the solid S. Our intuition tells us that our approximation becomes better as m and n become larger. And so we expect that as we take the limit as m and n approach infinity, we no longer have just an approximation of our volume, but we get a quantity that equals our volume. Again, we have a lot of cumbersome notation here. A limit as m and n approach infinity, two summation signs, subscripts I and j, stars and deltas. This is too much for us to carry around, so we change notation. We replace the limit of the sum with integrals. Because we have two sums, they become two integral signs. We drop the subscripts and the stars and just have f of x, y, and we replace the delta with the letter d. We use the expression in this equation to define the volume of the solid S that lies under the graph of f and above the rectangle R. Now, limits of this type occur frequently, not just in finding volumes, but in a variety of other situations, even when f is not a positive function. So we make the following definition. We define the double integral of f over the rectangle to be the limit of the double Riemann sum if this limit exists. Now, if f happens to be a positive function, then the double Riemann sum represents the sum of the volumes of columns, as in the figure, and is an approximation to the volume under the graph of f and above the region R. Therefore, a volume can be written as a double integral. If f of x, y is greater than or equal to 0, then the volume of the solid that lies above the rectangle R and below the surface z equals f of x, y is found by computing the double integral over R of f of x, y. Here's an example. Suppose we want to find the volume of the solid that lies underneath the surface z equals 16 minus x squared minus 2y squared for x between 0 and 2 and y between 0 and 2. Here we see an approximation of the volume by 4 boxes. Here are other versions where we have m and n equal to 4, 8, and 16. Notice, the volume under this surface becomes more accurate as m and n increase. Now, let's do our very own example from scratch. Let's estimate the volume of the solid that lies below the surface, z equals xy, and above the rectangle R, where x lives between 0 and 6, and y lives between 0 and 4. We'll use a Riemann sum with m equals 3 and n equals 2, and take the sample points to be the upper right corner of each square. Here we go. Let's first sketch the rectangle R. We want x to live between 0 and 6, and y to live between 0 and 4. Since m is equal to 3, delta x is 6 minus 0 divided by 3, or 2. And n is equal to 2, so delta y is 4 minus 0 divided by 2, or 2. Note this also means that delta a, which is delta x times delta y, will be 2 times 2, or 4. All right, let's divide our rectangle accordingly. Notice that delta x is 2 and delta y is also 2. So our rectangle R looks like this. Now, we're told to take the sample points to be the upper right corner of each square. So in our very first square, the upper right corner will be the point 2, 2. Next, our upper right corner will be the point 4, 2. Then our upper right corner will be the point 6, 2. And we move our way along the top row of squares as well, taking each sample point to be the upper right corner. Then we estimate the volume of our solid by taking the volume of each individual column. So the height of each individual square is given by evaluating f at the corresponding sample point. So f of 2, 2, plus f of 4, 2, plus f of 6, 2, plus f of 2, 4, plus f of 4, 4, plus f of 6, 4. Those are the heights of each individual box. The area of each box is that delta A, which we found to be 4. Using the fact that in our example we were told the function was x times y, we see that the volume is approximately 4 plus 8 plus 12 plus 8 plus 16 plus 24 times delta A, which is 4. And so we get an approximation for the volume of 288. And that would be the end of this example. Now, up next, suppose we don't want to settle for simply an approximation of the volume. If we want to be able to calculate the volume exactly, then we're going to need to be able to work with those integrals. And that's the topic we'll deal with in class next time. Thanks, guys.